Hello everyone, it's my honor to introduce our ASC paper, Snopy, Bridging Sample Denoising with Causal Graph Learning for Effective Vulnerability Detection. Software vulnerabilities are weaknesses that could be exploited by a threat actor for a variety of malicious ends. As such weaknesses are unavoidable during the design and implementation of the software, detecting vulnerabilities in the early stages of the software life cycle is critically important. Prior studies rely on human experts or predefined vulnerability rules to search for security-sensitive operations. Recently, benefiting from the great success of deep learning in code-centric software engineering tasks, an increasing number of learning-based intelligent detection approaches have been proposed. Compared to conventional approaches that heavily rely on handcrafted vulnerability specifications, deep learning-based approaches focus on constructing complex neural network models to automatically learn implicit vulnerability patterns from source code without human intervention. While promising, current neural vulnerability detectors suffer from severe performance degradation when applied to detect vulnerabilities in real-world settings, posing a barrier to adoption. Such poor generalization ability stems from two major challenges. First challenge is noisy program semantics. Let's consider a real-world vulnerability as a running example. At line 15, there exists out-of-bounds right when the variable URI length is allocated to it without bounds checking, lead to local escalation of privilege. To fix it, developers perform compulsory security checks at lines 10 to 11 to limit the size of URI length to avoid writing past the end of the allocated buffer. As shown in this case, the core logic of a vulnerability generally involves only a few statements, while the whole function contains dozens, mostly hundreds, of lines of code. As a result, these program semantics of vulnerability-irrelevant code elements will heavily influence the deep learning model. To mitigate the noise problem, an intuitive way is to perform program slicing from vulnerability-prone program points of interest, such as sensitive API and pointer usage, to prune irrelevant statements. Despite their effectiveness, such preprocessing still relies heavily on the expertise of the developers performing the analysis and the knowledge of existing vulnerabilities. In addition, according to the annotation rules of existing vulnerability datasets, samples containing statements removed from vulnerability fixing commits are vulnerable. Thus, any code slice generated from this motivated example are benign, introducing the risk of error labels. The second challenge is learning spurious correlations. Recent works point out that existing vulnerability detectors can be easily fooled into flipping their decisions by simple perturbations such as identifier replacement. This is because deep learning models tend to pick up dataset nuances, such as specific coding styles for prediction. To cut off the correlations between spurious features and model outputs, state-of-the-art approaches either retrain deep learning models on program variance based on heuristics, or ignore the spurious features during the inference stage. However, current solutions focus on enhancing the robustness of detection models against the target samples with spurious features, instead of capturing real vulnerability patterns, resulting in marginal performance improvements. Based on the above discussion, an important question arises as how to capture real vulnerability patterns from vulnerable samples with numerous noise for effective detection. In response, we propose Snopy, a novel deep learning-based approach which combines sample denoising with causal graph learning for effective vulnerability detection. Motivated by the fact that current vulnerability datasets primarily connect vulnerable samples from vulnerability fixing commits, we propose a change-based sample denoising strategy, which conducts noise cleansing based on the modifications between vulnerable functions and corresponding patched versions to automatically weed out the noise information in the vulnerable functions. In addition, considering that vulnerability fixing commits may also contain vulnerable irrelevant non-essential changes, such as variable renaming and cascaded adaptations, we further leverage the state-of-the-art VSZZ algorithm to connect vulnerability contributing commits as references to confirm truly vulnerable statements. Our intuition is that vulnerability semantics persist and propagate across multiple versions, from the vulnerability introduction to the vulnerability patch of the vulnerable functions, regardless of other internal modifications, which are often benign. After that, we conduct noise cleansing to extract the vulnerability-related part, including 3 steps: essential line localization, selective context slicing, and purified samples generation. Following prior works, essential vulnerable lines are statements removed from patched functions but included in induced vulnerable functions and declosed vulnerable functions. Then we adopt a selective program slicing strategy to precisely extract vulnerability context. Like normal backward slicing, we preserve all statements that have influence on essential vulnerable lines with respect to data and control dependencies. As for forward slicing, we design 2 rules. First, performing data flow slicing as target statements receive variables or parameters assigned or checked by vulnerable lines. Second, if the previous forward data flow slicing result is empty, performing control flow slicing. To promote the detection model, learning real vulnerability patterns, we propose a novel causal intervention model with feature caching scheme. Given an encoded CPG, we first employ 2 MLP layers to calculate node and H-level attention scores as follows. Then we decompose the original CPG into the initial causal subgraph and spurious subgraph, and produce graph-level representations for them. Having obtained the representations of the causal subgraph and spurious subgraph, we would like the detection model being able to disentangle them during training process for better predictions. To do so, we employ the standard cross-entropy loss over the training samples to ensure the correctness of predictions based on causal features. For spurious features, we push their predictions evenly to all categories since they are unnecessary for classification. Causal intervention requires pairing the target causal feature per example with various types of spurious features that appear in the dataset. However, blindly traversing all possible spurious features is unrealistic because any attribute of the input dataset that exhibits static correlation with the target label can be abused. To address this challenge, we propose a novel feature caching scheme to reuse previously identified spurious features. In each training epoch, we feed more data into the batch size and store spurious features into the cache space. In the intervention stage, we combine the causal features with various spurious features and maximize the causal effect of real vulnerability patterns on predicting labels, regardless of changes in spurious parts. Our work seeks to answer 3 questions below. For evaluation, we compared Snopy with 9 state-of-the-art baselines, including 7 DNN-based approaches and 2 LLM-based approaches on 3 popular datasets. Here is the performance comparisons between Snopy and state-of-the-art baselines on the 3 datasets regarding the form matrix. The performance improvements of Snopy over the state-of-the-art approaches are positive. Particularly, Snopy outperforms the best performing baseline S4D by 2.35%, 13.20%, and 6.72% in FE score on the 3 datasets. As for the second RQ, the experimental results are presented below. On 2 large-scale vulnerability datasets with CWE information, Snopy produces substantial improvements of up to 21.80% and 20.78% in terms of FE score, on average, over the previous best performing baseline in detecting different types of real-world vulnerabilities. As for RQ3, this figure presents the results of Snopy and its 6 variants. We can find that both sample denoising and causal graph learning are essential for the performance of Snopy. The most important component of Snopy is the causal intervention module, that resulting at most 30.51% improvement in FE score. In addition, different weights of loss coefficients have varying impact on Snopy's performance, and the larger capacity of FZS module may not always guarantee better performance. Let's conclude this paper. In this paper, we analyze the challenges of existing deep learning-based vulnerability detectors and propose Snopy, a novel deep learning-based approach which bridges sample denoising with causal graph learning for effective detection. Snopy adopts a change-based sample denoising approach to weed out vulnerability-irrelevant parts of vulnerable functions. Thanks for your listening. We have open-sourced our artifact. If you have any question, please kindly contact me.